Hello and welcome to BRK ENS 2041 EVPN Campus Design and Implementation. My name is Sergey Nasonov, and I'm a solutions engineer based in Sydney, Australia. Yes, it took me 25 hours in the plane to get here just to talk about EVPN. This is how much I like it. But before we even start talking about EVPN, a couple words about the format of the session. So I always appreciate live questions. It actually means you guys are paying attention and still with me. If I feel I'm running out of time, I'll ask you to post the questions in the chat. I will be personally answering all the questions, and I also make sure that I will stay after the session for as long as it takes to cover all the questions in person. There are 3 slides in the session that are hidden. It's just reference slides, so have a look at the PDF after the session if you want to have more information. Now, the idea for this session had started when I was meeting a CIO in one of the large hospitals in Australia. That CIO, in a meeting, he said, Sergey, I want an EVPN fabric for my new hospital build-out. I don't know why, but you need to make it happen. Okay, fair enough. And I tried to make it happen. In the process of making it happen, I realized that there's not much public information available about the EVPN design and implementation on Cat9K. So naturally, I spent a lot of time and effort making it happen. At the end of it, I decided to make my work public, so you guys don't have to go through the same process as I did, making it work. So the goal of this session today is that every single one of you can walk out and implement a working EVPN solution in a campus using Cat9K, covering real use cases on real equipment using CLI, working CLI, I should say. Okay, how are we going to make it work? As you can see on the agenda, first half an hour will be EVPN crash course, just to level set for everyone. Once we have an understanding how protocol works, we look at the architecture and certain design trade-offs that you would need to do while making the EVPN design. Once we're happy with the design, we'll progress to the implementation. That will be a session full of CLI examples. And if time permits, we're going to cover the multicast operation and fabric overlays. Let's kick off. How EVPN works? Well, before we start thinking about how, let's think about it, what it is. EVPN, or Ethernet VPN, is just an address family in BGP, intended to carry layer 2 information, so MAC addresses, and the layer 3 information, IP addresses, over certain transport network. Why I say transport network? Well, because the original EVPN standard, as you can see, RFC 7432 in 2015, was released and was designed and released for carriers. Because carriers had enough of maintaining 2 different address families, VPN v4 for layer 3, VPLS for layer 2, they wanted one family. That's the EVPN. And as you can see, the solution was released with EVPN control plane and MPLS data plane. A few years later, the technology trickled down to data centers, and RFC 8365 was released with a VPN control plane and VxLAN data plane. That solution entrenched in data centers and eventually trickled down to campus. And that's exactly what we're going to be talking about today. I must say that EVPN keeps evolving, mostly based on the service provider requirements. So as you can see, OIM framework, EVPN SRv6, this is all mostly SP things. But what we have in EVPN is enough to make campus network working fine. So a famous quote by David Wheeler is, all problems in the computer science can be solved by another level of indirection, in other words, abstraction. That's exactly what EVPN brings to the campus. We're creating a virtual topology or virtual overlay on top of our traditional routed or switched network. So for the purposes of our discussion, we will look at the overlay. As you can see, it's a VxLAN encapsulation, and it needs a routing protocol. In our case, it's BGP with EVPN address family that runs on top of the physical network, the traditional network, how we call it, that uses Ethernet encapsulation and some way of traditional routing protocol, being ISIS, OSPF, or BGP. So before we start looking at EVPN, just one slide about the encapsulation part, right? So we're going to use VxLAN for our fabric encapsulation. The way that it's going to work is that we're going to have original layer 2 frame, all 1500 bytes. We slap a VxLAN header on top. In that VxLAN header, there is one interesting field, pretty much the only one that we care about, is a VNI, Virtual Network Identifier. This is our overlay ID. As you can see, in theory, that VNI field is 24-bit. So it allows us to give, it allows 16 million segments. With first 4,000 are not assignable, because 4,000 kind of VLANs, right? So 16 million segments sounds a lot, but the reality is a bit more harsh. And let's say Cat9K hardware can support up to 1,000 VNIs. So 1,000 overlays in the fabric. Okay, so we have our VxLAN header. We slap the UDP header in front of it, as per standard. UDP header is interesting because it introduces the concept of the ports. The destination port is 4789, which is the well-known VxLAN port. The source port is pseudo-random. It's just a hash of the original payload MAC, IP, TCP, UDP headers. So this is to introduce some randomness into the VxLAN headers so that we can do equal cost multipathing, right? Even if the destination source and IP are the same, is the next header, the destination port is the same, the source port is random per flow. So if you have multiple flows, they can be evenly distributed across multiple links, but you're not going to get out of order packets because every flow will be still hashed in one direction. Then, of course, in front of UDP, we'll slap IP header. And with IP header, there are two interesting fields there. The source VxLAN tunnel encapsulation endpoint, so our VTAP, and a destination VTAP. So the transport network only needs to know these two IP addresses in the outer header. It does not need to know anything in the original layer 2 frame and original IP addressing. That's what makes it a tunnel. Because you're using the Ethernet, we need to slap MAC address, MAC header, and forward it out. The key point is that these four headers combined add 50 bytes of overhead. So our transport network needs to accommodate that. If you have original packet as 1500 plus another 50, that's 1550 at minimum. Okay? Well, that's enough about the VxLAN. Couldn't be simpler, right? Let's progress to the EVPN part. So with EVPN, in the following slides, I'll show plenty of CLI outputs which were taken from this lab. As you can, and I wanted to make sure that you understand how this lab was set up and how it's supposed to work. So as you can see, it's a two-tier topology. We have our core switches and two pair of access switches. They're all VTAPs, so they're all running BGP between each other. We're not running a full mesh here, so it's just the core switches are BGP router reflectors. Because we're peering from a loopbacks, I need to use some interior gateway protocol to facilitate the convergence. In my case, I'm using OSPF. And crucially, every access switch has a VLAN 200 Anycast gateways configured. So the VLAN 200 is stretched across the whole environment. And I even have a couple of hosts in that VLAN, as you can see. Host on the left, .131 with the MAC address FA8. And there is a host with .130 and a different MAC address on the right side. So that's our original setup. Okay, so what happens when this host .131 comes online in the network? Well, the switch is going to pick it up. It has a MAC address for sure, because it's all Ethernet network. So the VTAP picks up the MAC address and it generates EVPN type 2 route. So there are there are 5 standardized route types in EVPN, and there are about 6 more that is drafts. But we only need to know about the 2 to make fully functional EVPN network. And the first one is a route type 2, which is carrying information about the individual host or endpoint. Right? Every endpoint has a MAC address. Okay, let's generate an EVPN type 2 route with the MAC address. Notice it doesn't have an IP address, doesn't have anything else. The /20 is not a mask. It is just the length of this BGP update in bytes. Okay? Okay, so we generated the MAC address. Sometimes this is the only information you can have about the endpoint, because maybe it's a non-IP endpoint. It uses the BACnet, for example, but it's still a MAC layer. So that's enough to make layer 2 overlays working. However, normally you will have an IP addressing, so endpoint might go through the DHCP process, or maybe it's a static address, statically addressed endpoint, and eventually the switch will pick up an IP address through DHCP snooping or through the ARP learning. It will generate a next EVPN type 2 route, this time MAC address and an IP address that it picked about this endpoint. Because it's a type 2 route, this 32 is actually a mask. It's a /32 host route about this endpoint. Now the control plane knows that this MAC address has association with the IP address. Additionally, if endpoint has IPv6, in my case it's a Windows VM, so by default it has v6 enabled, and it does have link local v6 address, EVPN control plane going to pick it as well, and it's going to generate type 2 route as well. What else is interesting? As you can see it here, next hop is 0. That's indicated it's a locally originated route. It's still BGP after all. This is how it works. But what we're going to see from the other side, on the receiving side, when this route is being injected into route reflector and reflected to the rest of the network, we're going to see more or less the same information. We're going to see the MAC address of the endpoint that it learned, the IP address and IPv6 address. Crucially, the next hop is now changed to the original loopback 0 address of the originating VTAP. But now we have all information to facilitate the unicast connectivity. Right? So if you have a remote endpoint willing to communicate with a particular host, the receiving VTAP can now have all information to build it, to build the VxLAN tunnel. Right? It has the destination MAC address or IP address and a destination VTAP. That's enough to send the packet. Or is it? What normally endpoints do when they're sending traffic to the endpoint that they haven't communicated before, they'll send an ARP, right? Or it could be some other BAM traffic, like link local multicast or whatever else. So let's look how the ARP is handled in a network. Well, endpoint wants to send an ARP. I'm sure you've seen it in Wireshark captures many times. Who has 1067.118.130? So we have an IP address, we don't know the MAC address. In EVPN Fabric, the ARP can be handled in two ways. Let me rephrase. The standard suggests of two ways of handling ARP. First way is EVPN proxy ARP. The way that it works is that the control plane, EVPN control plane, already has this binding. Remember? We already have a route that has a matching MAC to IP address. So if that mapping is present in EVPN control table, the source VTAP, where it just receives the ARP request, can immediately forge an ARP reply. Right? It already has the IP to MAC binding. Everything is great. That's how EVPN proxy ARP would work. EVPN ARP suppression works slightly differently. When you enable ARP suppression, all VTAPs build the ARP suppression cache, which maintains the same information. It's a MAC address and it's the IP address by snooping the ARP responses and replies. So in both ways, if the cache hit or control plane has this mapping, the source VTAP is going to forge the ARP response on the behalf of the remote endpoint. So ARP is not traveling. But what happens if control plane does not have this IP to MAC mapping? For example, there was no ARP communication, so ARP cache is not populated. Or maybe this EVPN type 2 route is just not present in the routing table. This is where the behavior differs. With proxy ARP just silently dropped. Notice that it's not flooded across the network, it just dropped. So if you have silent hosts and things like this, that's probably not the best way of configuring your overlay. ARP suppression, however, if ARP suppression cache is missed, it's going to flood this ARP packet in an overlay. Effectively, it's going to be a broadcast in an overlay. But how can we make broadcasts in an overlay? If it was a traditional Ethernet network, it's simple, right? You set destination MAC FFFF and forward it out gets everywhere. But we have routed transport network. How can we do it? Well, it turns out there are also two ways of doing it. You will notice the pattern. It's always two ways. So one way is the ingress replication. So the way that it works is that the source VTAP will receive this broadcast packet, will convert it to unicast, will send to all other VTAPs that have this overlay configured. And it's called ingress replication. So the advantages, it's extremely simple configuration. Just one CLI command, everything works. The disadvantages and additional advantages, there is no multicast state in your core network, which would be required for the other solution. Disadvantages, very low scale, right? Imagine if you have the overlay that is stretched across hundreds of switches, and in that overlay you potentially have 1,000 or more endpoints. Modern endpoints are very chatty. They can generate number of broadcasts per second, or link local multicast, and then imagine all of this stuff is just being multiplied by 100, because if you have this overlay configured on 100 switches, it will be tons of these parasite packets that would have to be generated. It's a put additional strain on the network bandwidth and also on the switching ASICs to generate these additional unicast packets. So this solution works on a smaller scale. If you're running the large-scale environment, I strongly consider to look at the other option, the multicast-enabled underlay. So this option works this way. You have a bump traffic for the particular overlay. You map it to the multicast group in an overlay. And then you let multicast to handle this efficient packet replication. So configuration is reasonably straightforward as well. You just map a specific overlay to the specific MAC, to the specific multicast group. Very high scalability. The downside, you actually need to have this multicast-enabled underlay, which means additional configuration, and most importantly, additional multicast state on your core switches. Some customers are not too happy with that. But if you have a scaling issues, then that will be the way to go. Okay, now we have enough information to actually build a layer 2 overlay in EVPN using CLI. Let's try to put it all together. First things first, we need to create a VLAN. This would be the VLAN that is facing your access ports for the endpoints, right? So VLAN is our foundation. In our case, it's a VLAN 200. SVI is optional if it's a layer 2 only overlay, right? Your endpoints might not be even IP endpoints. Maybe you have a gateway outside the fabric. So it's optional in that scenario, but you can still put it. What is not optional is to create a MAC VRF. Think about this. When we're talking about the VRFs, we typically think about the partitioning the routing table into multiple segments. That works for layer 3. But because we're creating a layer 2 overlay, we need to partition MAC address table. And that's why we're creating a MAC VRF, or in EVPN lingo, it's called EVI, or EVPN instance. All right? And as you can see it here, we're creating EVPN instance. The numbers can be anything, but I like to keep numbers consistent. It helps in troubleshooting later. And then we just need to bundle this VLAN. We need to put it into this MAC VRF. And to the resulting construct, we would need to assign the VNI. This is the VNI that will go into this VxLAN header. Remember that VNI field? This will be the number. Because first 4,000 are not assignable, you have to slap some number in front, but otherwise I still want to keep it consistent, so it's 200, 200, 10, 200. So the overlay is created. The next step, we need to create the VxLAN interface on the switch. It's interface NVE1, network virtualization endpoint. Don't ask me why. And in there, we simply borrow the IP address from a loopback. We're using EVPN, which is the BGP, as our control plane. And we're simply mapping our VNI, this layer 2 overlay, to the multicast group of our choice. The group number is arbitrary. You can use any group. If you wanted to use ingress replication, we, instead of mapping it to multicast group, we simply say ingress replication. Okay? And of course, The last but not least, we actually need to enable EVPN address family and configure the peering with our core switches. And that's it. If we had an SVI created, we would need to advertise this SVI as well into EVPN. Could not be simpler, and we're running our first layer 2 overlay. Isn't it cool? So behind the scenes, the way that it will work, once this endpoint is advertised into EVPN, this is the BGP output you're going to see in network. So what you're going to see are two routes. So as you can see, my show command references the MAC address. And we can see this is this type 2 route with the MAC address. Notice that there is no IP address. That may or may not come later once the IP address is picked up for that endpoint. And we can see there are two routes because we have two core switches that are route reflectors, so cluster ID is different. And we have our VNI. This is this layer 2 overlay ID where this MAC address belongs. You might be interested, why is it label and not VNI in the show output? Remember, in 2015, the original EVPN control plane was introduced with MPLS. So there are some leftovers in CLI like this. Okay, one important thing here, encapsulation is encoded as 8. That's a VxLAN encapsulation. And because we're dealing with BGP, route taggers are always present. For layer 2 overlays, route targets that export and import, they're generated automatically. So you don't need to manually define them. However, on iOS XE, they're generated in the format of BGP ISN, and this is an EVPN instance ID number. Different operating systems might use different automatic RTs. So if you try to mix switches in one layer 2 overlay, they might not work from different vendors. But you can always override this automatic generation to the format that you want. You just need to know where to look at. Okay? So we had our first layer 2 overlay, which is the VLAN stretched across our environment. Typically, we will have number of VLANs and a number of VRFs in our campus network. So let's have a look, how can we enable routing between our layer 2 only overlays? Well, if we're talking about the routing, we need to talk about the VRFs. And the concept that facilitates the routing between the VLANs in the VRF in a EVPN overlay is called layer 3 VNI. So layer 3 VNI is effectively a VRF ID for EVPN. So the way that it works is that it's configured on every switch where you have this VRF created. And during routing lookup, the source VTAP will recognize that the destination packet is outside of layer 2 overlay, so it needs to be routed. So it will pop this layer 3 VNI number in a VxLAN packet and send it to the destination VTAP. The destination VTAP, it receives the packet with layer 3 VNI, it maps it to the local VRF that it has, and it can do local routing lookup and send it to the VLAN that you need. Okay? So those of you who worked with VPN v4 MPLS VPNs will immediately notice the similarity of this L3 VNI concept with the inner MPLS label. Right? MPLS packet will have two labels, one the outer, changed hop by hop, and once you get to the destination PE, you will look at the inner label to identify the destination VRF. This L3 VNI works exactly the same way because it's designed by the same people that designed the VPN v4 RFC. So, how did it work in CLI? As you can see, the VTAPs now will announce a subnet. Not a host, but a subnet. And because it's announced a subnet, now we have a EVPN route type 5. That's the second and the last route type that we need to know for the purposes of today's presentation. So route type 2 carries individual endpoint information. Route type 5 carries the subnet information. So it carries a subnet, so you can see it here, 10.67.118.128. The mask is in front, not behind. Don't ask me why. It is what it is. This /17, again, is just the length of the BGP update in bytes. And we have two different hops, two different route reflectors, again, different cluster IDs. All other attributes are similar to to the previous one. So now we have enough information to piece together a routed overlay, or rather VRF with multiple overlays. So when we're talking about the VRFs, we need to define an IP VRF now. As you can see, VRF definition, we need to put the RD. Now you can see there are two types of route targets. There are normal ones, and there are ones that are ending with the word stitching. What's the difference? Well, the stitching ones are used exclusively in EVPN address family. So when you're exchanging information inside or between your VTAPs, the stitching ones are used. But at some point, your fabric needs to communicate with the outside world using VRF Lite or MPLS, and this is where the normal route targets come in. I hope it makes sense. Then we need to define the core VLAN. And frankly, when I started doing EVPN, that concept took me the most amount of time. So I would appreciate full attention for the next 30 seconds. So here's the idea. Remember when I said that layer 3 VNI identifies a destination VRF on the destination switch? So this is what we need to do here. We first create a VLAN, just a normal VLAN. This VLAN will never have any users in it. And we're creating this VLAN so that we can create an SVI. So we create an SVI and we put it in our destination VRF. Notice I said this VLAN will never have any users. It will not be on the trunks. So this SVI will never come up. So what you would need to do is put no auto state to force it up. Because what we're going to do next, we're going to map this SVI, this 1099, against our layer 3 VNI. You see? The puzzle completed. Traffic arrives in VNI 1099. The switch now knows it needs to route it through VLAN 299 because we mapped it together. And VLAN, the SVI 299 belongs to the VRF medical. Aha! This is where I would need to do routing lookup now against all other layer 2 overlays. That's pretty much it. The last step is just we need to map our L3 VNI under our VxLAN interface. And of course, we need to advertise it in EVPN under BGP peering. That's the most complicated concept in this presentation. Now we can all relax and start sleeping again. However, there is one more thing in the theory part. It's a connecting to the outside world. All right? So far, we configured our EVPN overlays. At some point, we need to connect to the Fusion device or to the firewall. So we normally refer to the VTAP that does this outside connectivity as the border. That border VTAP function can be the same. That can be collocated on a core switch, or you can have it dedicated. Both options are perfectly valid. And we connect to the outside world using a VRF Lite handoff. And the configuration is reasonably straightforward. We need to create a VRF, obviously, if you're doing VRF Lite handoff. We need to configure core VLAN and VNI. So this is the same as on the previous slide, as you do it on the normal routing VTAPs. We configure VTAP interface. Notice that there are no layer 2 overlays or anycast gateways are created on the border. You simply don't need them. Our core VLAN will be our routed hop out. We don't need any other overlays here. And then, of course, under BGP, there would be two parts. There would be EVPN-related part, which is exactly the same as on the previous one. So we simply create EVPN peering, and we inject our VRF information into EVPN. And then on the bottom, we have the part that is related to the outside world. Normally, you would want to have a summary of your subnets, suppress individual host routes, just advertise the summary for the outside world. And then the last 5 lines are mostly, it's just a normal BGP peering for outside, right? This is my outside neighbor. As you can see, it's a different ASN. I would configure BFD to speed up convergence, and I would put some route map to filter stuff that I don't want. Okay, as promised, 30 minutes of crash course, and we're just on time. Now, once we know what EVPN is, in 30 minutes, we can actually discuss some EVPN campus-specific architectural choices that you would need to make in your campus design. But before we even start, a couple of words about the leaf and spine and 3-tier architecture. So as we know, EVPN had been hugely popular in a data center. In data center, on the left, you're seeing a classic leaf and spine topology. In data center, the most traffic patterns are east-west. You put so it's all the VMs, all the containers that are sitting in DC talking to each other. And that's why the leaf and spine architecture is highly east-west optimized, because you just rely on ECMP to get the packets between the servers. In campus, however, especially in the large ones, typically you're going to have three-tier architecture. Right? You're going to have your campus core, and then multiple buildings. Each building will have a couple of distribution switches, and number of floor access switches. And the campus architecture is north-south optimized. Typical campus flow pattern is that 5% of traffic is east-west, 95% is north-south. Okay? So, and as such, the campus architecture has three distinct layers, and we all know them. It's a core, distribution, access. And that's exactly the words I will be using going forward. So, now once we have an understanding of campus architecture, and we start thinking about EVPN, we will be presented with two distinct choices. How far we can extend the fabric? Can we extend it to the access layer and configure our VTAPs at the access? Or we have to restrict ourselves to the fabric to distribution and then have layer 2 access. Both options are perfectly valid, and each comes with the baggage. So you would need to carefully assess which one better fits your requirements. So let's have a deep dive on each option. Option number 1, layer 2 access with MLAG. MLAG is mandatory because you want to have a multi-homing from your layer 2 access, right? But first things first, advantages of this approach is the familiar layer 2 access. Straight from CCNA textbook, all the stuff from spanning tree, UDLD, VLAN, port channels, it's all there. We've been doing it for tens of years, I guess. Additional advantage, it is cheap, all right? Because the layer 2 switches, they don't need to be VxLAN capable, so the ASICs can be cheaper. Layer 2 licensing typically is cheaper than layer 3 licensing. Less scaling issues, which I will touch on. So the advantages are clear. What's the disadvantages? Well, disadvantages are more or less an extension of the advantages. Yes, it's a familiar layer 2 access. Well, to be honest, I just hate dealing with it. Again, spanning tree, UDLD, all of this stuff, been there, done that. Number of problems it causes sometimes is just astronomical. Additional problem is that if you have layer 2 access, it means you need to do MLAG in one way or another for your layer 2 access. And more or less you have two options. Tried and true stack-wise virtual, where you stack two switches, you closely couple them so that they create a single control plane, which is effectively a single logical point of failure. Or if you don't want to have closely coupling, you can loosely couple them using ESI multi-homing, which I'll touch on a bit later. But in a nutshell, this is the cutting-edge capability. The iOS XE that enabled support for ESI active multi-homing is 17.18.2, released in December 2025, so a month ago. And it has a reasonable learning curve and a configuration complexity. So that's so if you want to have the layer 2 access and the fabric to distribution, that would be the summary of the things that you need to keep in mind when you're doing this design. So layer 2 access, layer 2 protocols, you need to choose between stack-wise virtual or ESI multi-homing on your network. If you want to go ESI multi-homing, consider BGP convergence implications. Think about this. Every endpoint in the network generates 3 type 2 routes. If you're doing ESI multi-homing at your building distribution level and you have a skyscraper with 100 floors and potentially tens of thousands of endpoints, each generating 3 routes, all of that stuff needs to reconverge in the event of one of the boxes failure. That takes time. This is not a sub-second process. However, that design also allows you to do eBGP for underlay and eBGP for overlay. as written in RFC 7938 by Facebook. Well, Facebook operates large-scale data center, and that RFC will tell you it's only relevant when you're doing hundreds of thousands of servers in a single DC. The reason why they went BGP there is because the IGPs rely on flooding to propagate information. Right? If you have too many switches in your areas, the flooding becomes very inefficient. It just consumes too much of the switch's CPU, so they had to fall back to BGP to avoid that scenario. Well, the problem is that if you're using BGP in the underlay, you need to have a number of hacks to make it work. You need to hack its loop prevention mechanism and so on. So this is all very well described in this RFC. Have a read if you want to have a deep dive there. This session will mostly focus on OSPF or ISIS as the underlay routing protocol. So an alternative to fabric to distribution is fabric to the access, which means you need to have routed links all the way to the access layer. Advantages are clear. Because we have routed links to the access layer, there is no layer 2 protocols. Right? So everything is just point-to-point routed links, just like in our alternative solution, the SDA, which is based on the Lisp. Importantly, the switches don't need to be loosely or tightly coupled in a distribution or core. It's just pure routing, just pure OSPF or ISIS. So no single point of failure, rapid network convergence facilitated by things like BFD. The downsides. Automation is highly desired. Think about this. Typical campus network will have between 5 and 10 distribution blocks. That's your buildings, all right? If you have 10 distribution blocks, that's 20 switches. Sure, you can configure them through CLI. That's not too many. But the same network that has 20 distribution switches will typically have thousands of access switches. And configuring those thousands of access switches with EVPN overlays, well, that's a very tedious task. As such, automation is highly desired. An additional, less obvious problem is that you really need to think through your overlays. Otherwise, your switch TCAM might have a problem with you. Let me expand on that. Think about this. When your access layer are your BGP speakers, are the VTAPs, the BGP will naturally learn all information, all routing information from the whole network, and will try to install it in a routing table. Right? So every single switch will be, well, and what it will make is that the whole fabric will be limited by the TCAM scale of your access layer switch, of your lowest VTAP, effectively. And the way that it works is that each switch will have a host route table. So 9300 switch has a 24,000 host table. And you will populate all the endpoint information in the host portion of this TCAM. But let's look how it's being populated. Well, we saw it before on my show outputs. Once endpoint comes online, one host route will be consumed to learn about the endpoint MAC address. If you have IPv4, well, that's another host route. So suddenly our 24,000 host route table is divided by half. So you only can support 12,000 endpoints. Things get much worse if you have IPv6. As you said before, link local address generates type 2 route, goes into TCAM. Then you assign IPv6 global unicast address to the endpoint. One more goes into TCAM. And then modern operating systems, they're using rotating IPv6 address. So they will derive its own IP address from the one that you assign to them. It will be the third IPv6 address. So suddenly, from 24,000 hosts, you might be getting less than 4,000 hosts in your environment. Well, that's a bit too small, isn't it? Well, this is where we have to be smart and put this extra design work to increase the scale of our fabric. The way that we would need to do it, main principle, route everywhere. All right? So, and when I say that, remember this EVPN proxy ARP that doesn't allow flooding in the overlays? So you don't need to learn this MAC address only routes because they're dropped. Okay, use EVPN proxy ARP. Suddenly, you will have twice more space in your TCAM. The downside, you cannot use it everywhere because there would be some endpoints that rely on flooding, silent hosts as an example. Another interesting design trick is that you can contain the subnets to distribution blocks. Let me give you an example. Let's say you have a VLAN 500 that is stretched across everywhere, and you put 10,000 hosts there. 10,000 IPv4 hosts will consume 20,000 host routes, so you're pretty much full, right? 10,000 would be your network capacity if you stretch it everywhere. But what happens if you put these 10,000 hosts into VLAN 100? Well, these 10,000 hosts will only consume TCAM on this side. Then you put another 10,000 hosts on VLAN 200 on another distribution block. Suddenly now your fabric capacity is 20,000. And you can keep adding your distribution blocks. Because what happens between the distribution blocks, instead of sending all these /32 routes, we can just summarize into type 5 route and send a subnet, if the subnets are different between distribution blocks. Typically, wired endpoints don't need mobility. They can be contained within a distribution block. So what I'm trying to say that restrict the number of stretched segments. It's still possible to do, but use it case-by-case basis as an exception rather than a rule. I hope it makes sense. So to summarize fabric to routed access, the key design constraints that you need to think about, that we'll typically use IGP as the underlay routing protocol. Keep in mind that when you're doing OSPF or ISIS, 250 switches is the maximum recommended limit for Cat9K switches to be in a single link state area. If you have more than 250 switches, just use multiple areas. Let's say an area per distribution block. Perfectly working. You might be tempted to use IP unnumbered to simplify all these point-to-point link addresses. So IP unnumbered works in a way that you configure a loopback 0 interface with unique address, and then all point-to-point links just borrowing this address. It doesn't matter if the addresses are different on the different ends of point-to-point link, because it's a point-to-point link. Whatever you send there will arrive on the other end. So everything works with that approach. So OSPF, ISIS, multicast, VxLAN, everything works except BFD. So if you want to go that route, you would need to rely on IGP timers for failure detection. Might be a bit too slow for some. In routed access, you typically want to have a multicast-enabled underlay for BAM traffic replication. I think it goes without saying. It's just too many VTAPs. The scale might be prohibitively expensive for the ingress replication. And advantages is that there is no stacking, no close coupling between core and distribution. Automation is highly desired. Okay. We got our design done. Now we understand all our design choices. Next step, let's get to the implementation. When we're doing the implementation, we start from the underlay. The underlay starts with the MTU. Remember, the VxLAN adds 50 bytes MTU. So system MTU 19100. Different Cat9K switches have different maximum MTU value, but 9100 is the lowest common denominator. So feel free to use that. The next step is to create loopback 0 interface. As you can see, this is both routing for the BGP, management for SSH, and for VxLAN, and also for multicast as a PIM source. You might see in configuration guides that people can create 2 different loopbacks, loopback 0, loopback 1. You don't need to do it. Loopback 0, just a single loopback for everything, works fine. It's officially supported configuration. As you can see, it's a host route there. Underlay routed interfaces, nothing fancy, just routed links. You can use /31, /30, whatever you want. Once it comes to OSPF, so I'm using OSPF here, but if you want to deploy ISIS, it will be exactly the same concepts. Non-stop forwarding, you better enable it. It's not enabled by default, but if you have a chassis switches or XFSU or something, better to have it enabled. Reference bandwidth, again, IOSXC default probably from 15, 20 years ago, still 100 meg. And that's in a day when you can have a 400 gig interfaces in iOS XE. So 400 gig is what I chose. You can choose whatever you want. Fast reroute makes sense to amplify the convergence time. And then default information originate, you only put it on your core switches to inject a default route into your IGP domain. The last line will give time for other network protocols to converge after switch boots up. So that line basically will tell OSPF that this switch is not a preferred path, even though you converged already, for 60 seconds to allow other protocols to converge, BGP, multicast, MVPN. Yeah? So after 60 seconds, the switch will become active in OSPF domain. Importantly, the Ceph by default does not include the ports into load balancing algorithm. And we rely on a UDP source port for randomness. So Ceph optimizations, load sharing algorithms include ports. Same for IPv6, same for port channels if you have them in your network. Okay? The next step, and by the way, I'm talking about the routed access topology, but equally the same thing applies to the fabric to distribution. Right? You just don't configure these boxes and everything else remains the same. If you want to configure multicast for underlay, for bump traffic, it does not have to be complicated. Right? All you had to do is to configure anycast RP, so rendezvous point loopback, and anycast means it's the same IP address on both cores, advertised as loopback out. That would be our rendezvous point IP address. Configure MSDP, which is basically one line between the core switches so they can exchange a multicast state between each other because they're running anycast RP. And then you can enable multicast. So multicast routing, you put the RP to this anycast address, PIM register source, loopback 0, that's important command. Otherwise, it can be anything. And if you want, again, you can do the multipathing for the multicast. As you can see, multicast does not have to be complicated. It's literally 4 or 5 lines in a config. The next step is to configure BGP. All right? So in our design, as you can see, we have routed access topology, so our access VTAPs appearing directly with the core. These ones are just sitting in the middle. If you have fabric to distribution, you will just do this configuration on distribution switches. So with BGP, there is one interesting thing that you need to be aware of. BGP is indirect peering. We're peering from loopback on access to loopback to the core. So we have to rely on the BGP timers for failover. BGP timers, 3 minutes. All right? That might be a bit too slow for our tasters. Natural suggestion how we can improve it, BFD. But BFD, in this case, we would need to use multi-hop BFD. We're peering from loopbacks. And multi-hop BFD for BGP is not supported on Cat9K. What can we do? Well, there is an alternative for it. And the alternative is to use the host route tracking for BGP. So the way that it works is that you define the subnet with all your loopbacks where you're doing a BGP peering. You put this prefix list into the route map, and then you reference this route map in the BGP configuration. What it will do for you is that now BGP process will track the presence of the destination host route in a routing table. The destination loopback route is supplied by OSPF. And OSPF can be rapidly converging. So let's say if core 2 disappears suddenly, the loopback of this core 2 will disappear from routing table because OSPF will converge sub-second, which means that loopback 0 of the core 1 will disappear from the routing table on the access layer, which means the BGP will take the session down instantly instead of waiting for 3 minutes for that time. Another interesting consideration is that, as you can see here in configuration example, I'm using the templates for peer policy and the peer session. The reason for it is that if you potentially have hundreds of access switches, it's hundreds of BGP sessions to configure. And then imagine you would need to change some parameter there. You don't want to go and modify 100 sessions, but if you just create the templates and assign those templates to the BGP peering sessions, you just modify a template once. And once you created this template and configure this host route tracking, next step is trivial. You just configure BGP, you have the neighbors, activate EVPN address family, and configure our VxLAN interface. Notice I said hundreds of BGP sessions on our core switches. You might be tempted to use BGP dynamic neighbors on these core switches instead of configuring these 100 sessions manually or through automation. You can do it. BGP dynamic neighbors work. The downside is that the troubleshooting will become a bit more complicated because for me, the first step on what I'm doing when I'm troubleshooting BGP, I'm checking if the session is up or not. And when you go to the core switch and type show IP BGP neighbor, you will not see the down sessions with dynamic neighbors. Dynamic neighbors only show the up sessions. So that's pretty much it. So once we configured BGP, once we configured underlay, loopbacks, we configured multicast, routed links, and BGP, we're done with our infrastructure in the fabric. Now we can progress on making the overlays. And the first example is layer 2 only overlay. We touched on this in a previous part of the session. So layer 2 overlay can be configured on, or layer 2 only overlay can be configured on every access switch where you need to. It supports IP and non-IP traffic because it supports flooding. And the way that you would do it, under global EVPN configuration, you will set the replication type static, which actually enables a multicast replication. Don't ask me why it's static. And then you start creating the MAC VRF. You will create a VLAN. You associate the MAC VRF to the VLAN and assign a VNI number. And then you put this VNI number and map it to the multicast group. We've seen it before. Very simple to do. And you're already going in your fabric. If you want to add routing, there are two scenarios. Well, think about this. Normally we have VLANs, number of VLANs in the fabric with the gateways inside the fabric that are configured on multiple switches. That's what we call anycast gateways. Right? If we have it on multiple switches in the fabric, we call it distributed anycast gateways, or DAG. You will see this DAG abbreviation sometimes in my configuration examples and EVPN configuration guide. So the important distinction is that these anycast gateways can be breached, so they will support flooding, and they will be routed only, so they don't support flooding. If you remember from the first part of the section, to make it breached, we need to enable flooding suppression, and we need to disable proxy ARP. Fortunately, that's a default state. So when you're creating an anycast gateway, it always comes up as breached, as the lowest common denominator, I guess. So how can we make it? We create layer 2 only overlay, which is shown on the previous slide, and we simply add a layer 3 part to it. Layer 3 part starts from the VRF. So we create a VRF, we give it RD and route targets. We have our core VLAN and core VLAN interfaces. We have our layer 3 VNI, and we mapped our layer 3 VNI under the VxLAN interface. That's the bits that you would need to do along with the advertising this into EVPN. That's the bits that you need to do once per VRF. Right? So when you have, let's say, a VRF with multiple anycast gateways, multiple VLANs if you wish, you create the path that you shown on the previous slide once. Once you created the VRF and the core VLAN and advertise the whole thing into EVPN, all you had to do is simply create anycast gateways. Notice that I'm using a static hard-coded MAC address. Can you use the random one, the system MAC? Yes, you can. That will consume a little bit more TCAM resources to translate this, to carry these additional unique MAC addresses in your network. So my recommendation would be just to use the hard-coded MAC. You're already configuring the whole thing. This is just one more. And in my example, I'm just using 000 layer 2 VNI. Kind of makes it simple to troubleshoot later. If you want to ping your Anycast gateway from outside the fabric, you would need to enable advertisement of this Anycast gateway in your EVPN VxLAN. This is additional line. As you can see, this is the configuration that you would do under this MAC VRF configuration, or EVI. OK, we just created our Anycast gateway that supports flooding across the network. So with ARP suppression enabled, with proxy ARP disabled. If you want to conserve our TCAM space, we need to do the opposite. We need to disable flooding suppression, and we need to enable proxy ARP. This way, the MAC-only EVPN Type 2 routes are not generated anymore. So instead of having 2 host routes per endpoint, per v4 endpoint, we now have only 1. How can we do it? Well, we just create a bridged Anycast gateway, as shown before. And now we simply do these 2 things. We disable flooding suppression, and we configure EVPN proxy ARP. As I said before, that configuration works well with the conventional endpoints. If you have legacy endpoints or some tricky endpoints that are silent hosts that rely on flooding, maybe you have an application that still uses broadcasts or link local multicast to talk to the outside world, then routed Anycast gateway probably is not the best option, and you better go back to the bridged one. Sometimes you might be, or your business might be asking to configure a centralized gateway. Or maybe that would be the best way to implement it. So centralized gateway works where you create a bunch of layer 2 overlays on switches, and on one particular switch, that will be a handoff for that overlay. Let's say you have a service block here, and maybe you have a firewall, and you're just creating this one VLAN that needs to go through the firewall. In this case, centralized gateway would be the way to go. And advantages of centralized gateway is that most of the switches that you will have only layer 2 overlay, which is very simple to configure. Just a few lines. You don't need to create VRF or anything like that. Only on your centralized switch, you would need to create a VRF. You would need to create our core VLAN the same way as before. And all the same settings as with Anycast gateway. The difference is that on the VxLAN interface, you need to add the keyword local routing. That's what will make it a centralized gateway. Everything else is the same as in with Anycast gateway. Now, if you want to use ESI multi-homing in our network, let's say we have fabric to distribution and we want to do the multi-homing, I'll say one thing. First of all, have a look at the BRK NS 2473. It was aired yesterday, so if you missed that, watch the recording once it becomes available. So I'll just give you the glimpse of it, because that session was 60 minutes itself, just for multi-homing. I'm going to give you a 30-second version of it. When you're configuring multi-homing, typically you will do it for distribution switches. So you would need to have a direct L3 link between these distributed switches, and you will run additional BGP session between these VTAPs. They will form a cluster, if you wish. The reason for it is that with ESI multi-homing, once you enable it, it will generate a EVPN type 4 route for every combination on a VLAN host in a port channel, just like in spanning tree with virtual ports. So potentially you're looking at additional, so you have all of these type 2 routes for endpoint, and then you also have hundreds of additional type 4 routes for ESI multi-homing. What you don't want is to have these routes that are only relevant for this pair of devices are being propagated to the rest of the network. So you need to filter it out. That's why configuration is reasonably complicated. But if you just wanted to do it in a lab and you only have one pair, this is all you need to do. So you would need to configure this additional direct peering between them for faster failover. So the traffic, let's say if without this link, that switch fails, or that link fails, but traffic arrives to this switch, so instead of forwarding it back here, it will just use the direct link to transit. And the configuration is, as you can see, there is some multi-homing config under the global configuration, and then on every port, both uplink and downlink, you configure EVPN multi-home core tracking for loop prevention. And the line that actually enables the port channel is this EVPN Ethernet segment blah. Now you can configure the same port channel configure on both switches facing the same layer 2 access switch. So from layer 2 access switch, it's just a normal port channel. So if you configured VPC before, it works the same way. Okay, we might be tempted to think that we are done with our fabric configuration. And if you're just doing a lab, that's probably all you need. However, in production, there are a few more services that you need to enable for your EVPN fabric. First one is DHCP. So with DHCP, there is always a problem when you have anycast gateways, all right? So the traffic hits the SVI forwards it to the DHCP server. The DHCP helper puts the SVI IP address in a GIADR field, but you have maybe 10 of those switches with that GIADR address. What switch should receive the DHCP response? Well, there are two options again. Option number one, you would need to configure a loopback on every VTAP with unique IP address in that VRF where you're doing a DHCP service for, and that loopback will be your DHCP relay source. This way, the response will always come back to the switch that requested it. The downside, well, that's a loopback with unique IP address on every switch in every VRF where you enable DHCP. That's a lot of loopbacks. That's a lot of work, additional work. An alternative is to configure to already use existing loopback address, which we already have with unique IP addresses. That's our loopback 0. Just use that as a DHCP relay. And that's the option I'm going to show you. So first, every switch, this is the instructions on how to compose the DHCP packet. We need to insert option 82, VRF ID, things like this. Then, DHCP relay is the loopback 0. Importantly, with EVPN, one of the ways to build this EVPN type 2 routes for MAC address and IP address in the same route is DHCP snooping. Because this is how the IOSXC will learn this mapping. So if you're enabling DHCP, please enable DHCP snooping. And then you just configure helper addresses on your anycast gateways. It's important to use the word global because your loopback 0 in a global routing table. This is where it will send it out. So the DHCP packets will come in an underlay, not in an overlay for the DHCP server. So I tested it on Windows 2018 R2. It worked fine. So I assume it would work everywhere else. Another interesting use case is the microsegmentation, the TrustSec. So the TrustSec support came to EVPN Fabric about 2 years ago. And the way to make it work, there are 4 steps that we need to go through. First, we need to actually configure radius and TrustSec relations from the switch, between the switch and the ICE. Then we need to enable .1x map on the switch itself and configure respective policy in ICE to assign VLAN and SGT. And then the last but not least, the switch needs to be able to download the security group access lists and enable the enforcement for those. So let's look at it in a detail. So first, we need to configure radius and a TrustSec connectivity between the switch and the ICE. Notice, I'm showing you the puckless configuration. Why is it important? So when TrustSec was released in 2008, it was using PAC files, so protected access credential. It's like a cookie. So ICE puts a cookie on the switch using this cookie to talk to ICE to download TrustSec information. Everything is great, but this PAC method is using TLS 1.0, which is considered insecure, and a lot of organizations are phasing out this approach. As such, Cisco developed a packless authentication that is using TLS 1.2, so it's perfectly secure, perfectly fine. This is what I'm showing you. So it's a normal AAA config with radius. This line, the CTSM list, is the one that enables the packless authentication. The last bit that you need to do is to configure TrustSec credentials in the switch enable mode, username and password. And would be the same username and password that you will type on ICE when you're creating a NAD device with that IP address. I normally just use the switch serial number for username and password, but you can use whatever you want. All right? The next step, once we establish the radius, we configure the radius, is to do .1x or map. So I'm sure you've seen it before many times, so I'm not going to be focusing too much on it. Just a standard .1x template. As you can see, it's referencing a service policy. It's a following slide that I hidden because it's just a wall of text. If you want to deploy it later, you can just reference that hidden slide. But it's basically just .1x first. If it fails, then go to the map. What it makes us to do that when the endpoint comes online, the template from a previous slide will send stuff to the ICE. ICE will authenticate it, will assign some profile. It could be the VLAN and SGT. So far, so good. The problem is that for the enforcement, this will be the source SGT. All right? If you have an endpoint that receives that SGT that talks to another endpoint here, the destination switch needs to be aware of that SGT that is assigned to that switch. The way to do it, we carry that security group tag in a VxLAN header. Remember, VxLAN header had VNI field, that's for our overlays, and one field in front of it is the GPO, or Group Policy Object. So that's a field that will populate with SGT. To make it happen, on the VxLAN interface, just add group-based policy setting. That will make the switch to put the security group tag in a VxLAN header. The last step, we have our SGTs assigned, and the SG ACLs are being downloaded. But we actually need to enable enforcement explicitly. So the first line to enable, CTS role-based enforcement. That actually makes enforcement work, but not quite in the way that we wanted. By default, it enables enforcement on a routed interfaces and does not enable it on a VLANs. So we need to do the opposite. We need to disable it on routed interfaces because routed interfaces are facing the fabric. We don't want any user-facing stuff there. And we need to enable it explicitly per access VLANs. That would be our normal VLANs that are facing the users. Okay? The last step that I want to cover is this built-in limited loop prevention in IOSXE EVPN implementation. The way that it works is that if control plane detects a duplicate or MAC address or IP address move between the VTAPs within a certain period of time, it considers it as a loop. Think about this. If you have another switch stretched, like someone connected a layer 2 switch to both VTAPs in the same VLAN, and there is an endpoint sitting here, that endpoint will appear here sometimes, like the control plane will learn it from this switch, from this VTAP, and also from this VTAP. And this is a default values, as you can see. So 5 duplicates within 3 minutes. After that time, all the VTAPs will block this MAC address or IP address for the 5 minutes until they unblock it. So, or you can manually clear it. A question?
Block meaning
it will not.
data plane.
Yeah, it will not propagate it. It will not propagate it in so the question was, block means it will filter it in a data plane. No, it means it will not propagate it into the control plane.
And the loop will be going on.
Yes, but like if it's not propagated to the control plane, it means that the traffic between endpoints will not be forwarded in overlays anyway. So look, I guess the main important point here is that you might hit this problem if you're deploying distributed wireless. Right? So let's say Flex Connect style wireless, where the endpoints roam between the wireless access points. That would be the exact scenario where you might hit it, even without this link. And then your endpoints will be randomly blocked for random amount of time. So if you're hitting this problem, you can increase the values. So this is the default values. They're all configurable. Okay? So, well, I guess time permitted a little bit. So let's talk about the multicast in our Fabric overlays. Remember, the whole story started when it was a hospital. Hospitals do have a lot of multicast endpoints. It's patient monitoring, patient entertainment systems. They're all using multicast of various sorts. So when we're configuring multicast for EVPN, we're actually not using EVPN. We are using MVPN, so multicast VPN. That works exactly the same. It's an additional address family that was developed for MPLS VPNs to deal with multicast. So with EVPN, it works exactly the same way. So if you already worked with it in within MPLS environments, it works the same way. How it works? Well, we first need to create MVPN address family and run these peerings in parallel with EVPN peerings. Then under VRF, we would need to configure the default multicast distribution tree and data multicast distribution tree. So the way that it works is that the default MDT, it's our, well, I guess default multicast distribution tree exists on every VTAP where you configure it in this, and it's used for the low bandwidth multicast streams. So the way it works, similar to ingress replication, it just sends this traffic to every VTAP, irrespective whether it needs it or not. So it's useful, it's simple for low bandwidth streams. If you have a high bandwidth streams, for example, patient entertainment system is IPTV, high bandwidth, it would make sense to create a data MDT, which will generate on the fly a specific multicast group from the range that you define and carry that high bandwidth stream only to the VTAPs which need it, not to all VTAPs, which would be the case for the default MDT. Okay? And once you created it on a VRF level, the configuration is actually very simple. As you can see, we just enable multicast routing for a specific VRF. We enable source-specific multicast. It's very important, and I'm telling you because I spent a few hours troubleshooting it. Remember this core VLANs that we created for routing on all our VTAPs? You need to have PIM enabled under this core VLAN because the traffic, when it's coming between the VLANs in the same VRF, it flows through that core VLAN. So if you don't have it, your PIM RPF check will fail. So better have it. And then, of course, you need to enable multicast on interface SVIs. So if you just have a source-specific multicast, so without RPs, everything works already. But life is never that simple. And typically, you will have an applications that need to have ASM, so any source multicast, which will require a rendezvous point or RP configuration. And then, again, we have two distinct options. One is the multicast sources and receivers are in the same VRF. You might have some external sources and receivers as well, but as far as the fabric is concerned, multicast sources and receivers in the same VRF, not in different ones. In this situation, you can use Fabric Anycast RP. So the way that it works is that every VTAP will host that Anycast RP, so you will need to configure additional loopback, but it's the same IP address on all VTAPs per VRF. Then this loopback 0 in the underlay will be used for the source for the PIM joins. And if you do have an external RP, you just can configure MSDP from your border VTAP to suck information from outside. As you can see, configuration is relatively straightforward. One loopback per VRF with the same IP address on all switches, and then you just configure this Anycast RP for that VRF. Simple as that. Of course, there would be use cases when you will have a multicast sources in one VRF and multicast receivers in another VRF. This is also supported scenario. But in this case, you cannot use the fabric RPs, because if you use the fabric RPs, you would need to do multicast route leaking. And that functionality is not supported on iOS XE today. So what we would need to do is to use an external RP, so that that external RP sees all VRFs as potentially in the same global routing table. So then there is no route leaking. So the way that it works, as you can see, you would need to create a unique IP address per VTAP, per VRF. So it's the same scenario as with DHCP option 1. You create a unique loopback per switch that will be used as a source for PIM joins. All right? And then you simply point, so you create this loopback, and then you point every switch to some external RP. And you use that loopback as a source for the PIM joins for that specific VRF. Don't forget to enable PIM on your fabric handoff, so that when you're talking to the outside world, PIM needs to be enabled there. So this is perfectly supported scenario as well. Works well in my hospital. Okay, we got to the end of it. It was reasonably complicated topic, but there was only one question, so I hope I didn't lose you completely. The key takeaways that I want to get you from this session is that EVPN implementation on iOS XE on Cat9K switches provides flexible overlays that are layer 2, bridged, routed Anycast gateways, distributed, centralized, that can cover any use case that you can have in your campus fabric. EVPN overlays in a campus can be to distribution with layer 2 access, or to the access layer, and then you need to think about your TCAM issues. Both options comes with a set of caveats, no right or wrong answer, all depends on your business requirements, available hardware, and design capability. Functionally, as you saw it today, the EVPN fabric on Cat9K can do overlays, DHCP, multicast, loop prevention, multi-homing, and microsegmentation. Everything that I did in this lab was, everything that I shown on the slides was real. There is a hidden slide with the link to GitHub with full configuration listings for every switch and every use case, which you can use in your own deployments if you want. With that, if you like the session, please like and subscribe, or at least leave the good feedback. That's only 5, unfortunately. Continue your education, and thank you.